I'm dressed in aposematic coloration today to be warning predators away from eating me because obviously I'm toxic, like the 2003 hit from Britney Spears. Now, I'm mentioning aposematic coloration, but we're not covering aposematic coloration in this lecture. If you want to cover aposematic coloration, ecological stoichiometry, and herbivory methods of manipulating their hosts, you'll have to go back to topic number 9. Now, topic number 9 we did as a kind of an activity/lecture, and that is something you want to review because those terms are important for here, but I've already covered them. So we're going to move on to other topics of predation. So define, of course, predation. Herbivory we've already done, so just want to remind you, go back to that. Define the Red Queen hypothesis, parasitism, and parasitoid. Define terms in the Lotka-Volterra equations. Define ecology of fear, predator satiation, and refuge in size. Compare different forms of parasitism, and last, list and define theories of predation and parasitism. So I'm realizing also some of these later lectures that I've been videotaping, some of these late 20 number lectures, I'm actually over here in this black space below me and the topics are over there. That's something going on with Microsoft Excel. I like it a lot, but I don't really know why. So I don't know what setting has been changed in Camtasia. I'm just very thankful for it. But at the same time, if you see this big open space that I've created in every lecture slide, it's because I moved everything, so I'm not blocking anything. And then when I actually start filming, I know whether or not it's which form. Anyway, that's a little silliness, learning how to do this still. All right, so predation. We're looking again at this interspecies interactions. And predation, herbivory, and parasitism all fall under what we call exploitative interactions, where one of the organisms is going to suffer a population loss, and the other organism is going to enjoy a population gain. So that loss-gain relationship is going to be your exploitative, where one organism is losing resources and the other one is gaining them. So first off, take a moment. What do you think of when you hear predator? And since this is a film, I can just say, why don't you pause it and say a few predator names? So we usually come up with things like lions and tigers and bears. Oh my. Yeah. So we think large mammals that are going to be feeding on, well, smaller mammals, or more specifically, we think of predators that could eat, well, us. But we can think of predation in other terms too. We can think of, you've got your gazelle being eaten by the cheetah, of course. That's a clear predator that you probably thought of. We also have a rat eating eggs because the egg is technically a whole organism and the rat is devouring the whole organism. There's frogs eating insects. That's still predation. It's still organism eats organism, even if both are ectothermic. Giraffes eating seeds or eating fruit. It's going to be a predation interaction because the plant here is being technically preyed on when you're eating the seeds or fruit and you're not dispersing any seeds. A marmot eating flowers. Each pollen, remember, back from 142, each pollen is a whole plant, a whole organism, the gametophyte stage. So the gametophytes are being eaten, and to them, this is predation. Birds eating seeds, it's predation. An archerfish enjoying a little bug, predation. An amoeba swallowing up a ciliate, that's predation. A fungus capturing and eating a nematode, that's predation. And last, but definitely not least, a plant devouring insects, that's predation. So all of these are interactions that would fall under the broad heading of predation. When I look at beetles that eat seeds in my research, I'm looking at seed predators. And we define predation, and we're going to compare it to parasitism and herbivory by the duration of the interaction and by the level of lethality. A low lethality interaction that has a low duration is herbivory, generally. That's eating a plant. High duration, like a very long interaction between the two organisms, and a very low lethality would fall under parasitism. Parasitoids are those which are, predators are those which are highly lethal, but the duration of the interaction is very fast, especially when you're dealing with cheetahs. Now, parasitoids is something we'll cover later on. It's a high lethality and high duration of interaction. Quite fascinating, really. I love parasitoids. They're truly frightening. And we'll see this in terms of population effects. So we look at the story of the lynx and the hare. So the snowshoe hare populations would increase up and down. We have records of how many there were based on how many pelts were being delivered to the Hudson Bay Company. We'd see more pelts of hare or more pelts of lynx, depending on which one was more numerous at the time. So we'll see these long-term population cycles where the hare have a good year, and then the lynx would have a good year after it. Now, they are a little offset because hare and lynx have slightly different reproductive patterns. They have different levels of Rmax. Clearly, the hare is going to have a higher Rmax than the lynx, being a smaller organism that, well, they reproduce like rabbits. So you'll see these population cycles, and this impressive record really led ecologists to determine, is there kind of a way to mathematically model this? And that is where we get the Lotka-Volterra modeling equations. So the host population increases, and that's going to cause the predators to increase. But as predator increases, the prey population decreases. So I want to cover these in terms of what terms are used. So first off, we have the DNH, which is the change in the number of host organisms over unit time. And that's going to be equal to the R for the H times the N for the H. So that's your basic population growth equation. We're going to add a modifier, which is the rate of predation times the number of host organisms times the number of predators. P, NH, and P. And the P, NH, and P really says as there's a higher predation rate and a larger number of predators, even as there's a larger number of hosts, this whole quantity is going to get larger. And at some point, this quantity is larger than this quantity, which is going to lead to a negative DNH over DT. So that's going to cause your rate of your host population to change in a negative manner. Now, I want to contrast that immediately with the predator population, and that is a DNP over DT. And that is going to be equal to the conversion rate of prey into predators, and you have the CP, N, H, N, P. So instead of RNP, you have CPNP. So CPNP means this is your R, the conversion rate of prey into predator. So basically their ecological efficiency or trophic efficiency times how many are being captured times how many there are. And that is essentially RP. And then you're going to subtract the death of the predators, the death rate times the number of predators. So your predator equation is largely determined on this. And if this is very low, then your RP, this is essentially RP, your RPNP is lower than DPNP, then what you have is a negative DNP over DT. And that really means your births are less than your deaths. That's a simple way of putting it. And this will lead to cycles in predator and prey. We'll see this very simply. If you're modeling the predator-prey, you'll see these reciprocal oscillations in predator and prey populations. And you see they're very smooth. That's because these predator-prey numbers are not integrating stochastic factors such as just random genetic drift, the extinction of local populations, raindrops falling on mites, whatever. And we see this actually in a parasitoid-host interaction. This is mites on oranges, I believe. And what's going on there is they actually saw the parasitoid, which is similar to a predator, and the host, which is a host. And they saw these oscillations occurring for over 110 cycles. Now, they're not mathematically perfect. Again, you have this stochastic interactions happening. But if you limit the time axis, you get this circle. And the circle realizes there's an elliptical oscillation in predator-prey numbers. So modeling these out is pretty smooth. But of course, real life isn't pretty smooth just due to the roughness of real life. So that's predator-prey interactions in a equation nutshell. I want to move on to the evolutionary responses and the population responses, what we call refuges. So if prey interactions get too low, then you have essentially, at that point, you can have genetic drift, or stochastic factors can cause extinction. So it helps to have refuges for these populations, ways that the population can avoid predation, essentially a predator-free space. And one way is the metapopulation. Look back to your metapopulations, you'll see the same picture. Now, metapopulations are your series of different populations. So you actually will have a whole bunch of populations, some of which do not have predators present, some of which are going to have greater numbers of hosts. You can't have predators without hosts, of course, but this allows the recolonization of places that go extinct. So if prey goes extinct in one place, it can recolonize from another. So this essentially is a refuge. And it helps to have some places where the predators aren't, to allow the host population to kind of grow in the absence of predators. Now, eventually predators may find that, in which case they may look for another refuge. But you can always think of, in metapopulations, a slow-term run, a long-term running away from predators. You also have a refuge in predator numbers. Now, we covered predator satiation in topic number 9. I want to give some mathematics to that and some modeling here. Your probability of being eaten per organism is relatively low if the number of prey is relatively high. And a cyclical occurrence of prey, in the case of cicadas, it's a prime number. You'll notice that most of the cicada species are prime number species. And the 17-year, the 13-year, the 19-year cicada, these are prime numbers because it confounds the predator life cycle. There's no predator that can have a life cycle equal to that unless it is precisely equal to that. So a predator in 2-year life cycles is not going to encounter regularly the prey. A predator with a 17-year life cycle, okay, that doesn't really happen. If it did, they'd be very specific only to that cicada, of course. So this cyclical occurrence and the probability of getting eaten being low due to predator satiation, those are both ways of refuge in numbers. Another form of refuge in numbers is clustered or clumped dispersions. So a clumped dispersion utilizing a large number of organisms, during which some of them are going to be watching out for others and some of which are going to be feeding, is going to allow a refuge in numbers. Essentially, something's going to detect the predator as it approaches. And this is an advantage to clumping in dispersion. It's also an advantage for your RGB greater than C. So you'll find that clumped dispersions of organisms tend to be family groups, and that the organisms that are most related to others in that family group are going to be the organisms that are going to be giving off warning calls and watching for predators a little more often than ones that are, well, not related and will mooch off of the warning calls given by members of the species. So, or members of the population. So there is refuge in numbers, multiple ways. There's also the refuge in numbers of a large number of organisms being hard to track. It's hard to pick one out from a herd compared to picking one out from alone. So refuge in numbers can take many different forms besides predator satiation. There's also safety in size. An advantage for the herbivore is that because it exists on a lower trophic level than the predator, it inherently will have more food available to it. And since it has more food available to it, these organisms, especially ones with ectothermy, are going to be able to take in a larger amount of food for a lower metabolic cost. Remember that ectotherms generally have a higher trophic efficiency than endotherms. So having a higher trophic efficiency and having a larger amount of food available can allow the organism to just grow bigger. And eventually, a large prey is going to represent a certain level of risk to the predator. This risk has to get factored in to optimal foraging. We have here the snake approaching a toad. Now, the snake can easily eat the toad. It can easily go past the mouth parts. To convince the snake that this is not true, the toad inflates itself and tilts itself sideways to approach the snake to try to convince the snake that there is a risk associated with such a large reward. Although foraging has already occurred, capture is going to occur, and then digestion is going to be tough. If this toad is bigger than the snake, it's going to be impossible. So optimal foraging is hacked by increasing the prey size beyond what the predator can safely bring down, and basically saying, I'm too big, I'm not worth it. This is a very easy way of convincing a cougar that you're not worthy prey. If you are throwing rocks at it, if you're yelling at it, it recognizes a certain capture risk. Now, your kid won't be able to convince this because a child is obviously not a high capture risk, but a larger organism is going to be tougher to bring down. This is one hypothesis for the evolution of the sauropods. So these sauropods are very large dinosaurs that were essentially, we believe, they're too big for the theropods to bring down. So the theropods would simply avoid these huge sauropods because they're too much meat. And when they die, of course, they aren't spending themselves, and carrion eaters could become more common. But fast growth comes at its own price. Please refer back to the trade-offs and your life histories. So that'll be topic number 24. I also want to show this picture of mussels here. So the mussels of small size are not eaten because they're not worth it. But small mussels of some sort of minimal size become this optimal foraging because the sea stars can feed on them. It doesn't take too much energy to eat them, and you get high predation rate. But once the sea star diameter, since the mussel length is, say, over 14, only sea star diameters over 36 are going to be actually eating these mussels, and those are less common. So for most sea stars, they're not going to want to try or be able to try a mussel that is 16 centimeters long. So that is an escape from predation and a refuge in size. Now, refuges can come at a price. Time spent in a physical refuge is often time spent not eating. So herbivores will actually avoid high-risk scenarios when predators are present. So this is kind of fun. It's a double refuge situation. You have, let's take the example of wolves, elk, and aspens, or willows. So willows growing near rivers are going to be, they're going to be at high risk of herbivory by elk, because the elk will go next to the river. If there's no risk for them, the elk will go wherever the willows are and feed on the willows. Now, it turns out that these willows in and near rivers are good places for wolves to set ambushes. So this is a place where the wolves will have more cover and will be able to get closer to the elk. Since they can get closer to the elk, the wolves have a more optimal foraging. They don't have to spend so long in the pursuit. They do not have to utilize so much energy in the pursuit, and they can ambush the elk right next to the rivers. So, in the presence of wolves, the elk are going to prefer large open areas where they can maintain a good watch for wolves and where the wolves are not going to be able to sneak up on them. What this does is it means the elk spend less time foraging near the rivers, which means the willows now have an area they can grow without being eaten by elk. So it creates a refuge for the willows because this is where the wolves would be feeding on the elk. So you got a tritrophic interaction here. And also, eventually, like I said, the willows get so tall that the elk can't eat them. And when the willows get so tall that the elk can't eat them, you have refuge in size. Also, an ecology of fear thing is that in the presence of predators, herbivores spend less time feeding and more time and energy being vigilant. This is seen very well in an experiment with caterpillars. So what you have is I gotta read the graphs right. You have an herbivore is alive, a lethal herbivore alone, a lethal predator in the black bar, and a quote-unquote risk predator in the gray bar. The lethal predator here was a type of bug that can pierce the caterpillar's skin and suck out its juices. The risk predator was this type of bug, but they had ablated its beak so it could not pierce the herbivore, but the herbivore doesn't know that. So what you see is the caterpillar survival is relatively equal between it's not significantly different, I should say, when the risk predator is present versus when the herbivore is alone. When the lethal predator is present, of course, the caterpillar survival goes down. But the leaf damage for the plant goes down both in the presence of a lethal herbivore and in the presence of a risk predator. So a lethal predator and a risk predator will both bring the leaf damage down because the caterpillar spends more time being vigilant and less time feeding. Now you'll see the jasmonate and wild type and jasmonate insensitive and overexpressed. I don't want you to concern yourself with that. That's a great other story about plant defenses and a plant's ability to defend itself. And this is actually a really good paper, but the focal point of here is that a risk predator, the presence of a predator, even in the absence of feeding on the herbivore, can make the herbivore change its behavior enough to have an interaction, have an effect on the plants. Now, fear and feeding, that's taken off fear and loathing in Las Vegas, just in case you're missing the movie reference. This experiment was actually done in Ithaca. Let's talk about parasites. So parasitism. An endoparasite lives within the host, and an ectoparasite is going to feed on external surfaces. So something like a deer tick here is going to be an ectoparasite feeding on the external surfaces of the host. Whereas schistosoma trematodes, these are going to be feeding on the inside of the host, causing elephantiasis, I think. And you also see this kangaroo. I don't know if I hope I'm not going over it. Kangaroo is a type of catfish capable of following the ammonia stream from a fish's gills. And it'll follow this ammonia stream upstream, swim into the fish's gills, put out some spikes, and suck on the host's tissues. Much like the lamprey on this carp, this is an ectoparasite feeding on external surfaces. Then we see this most intimate interaction between vines and oak galls. So these oak galls are a small wasp, and the wasp will live inside the oak, causing the oak to actually provide more nutrients to the wasp in the form of this gall. It also forms a type of defense structure for the wasp. The oak gall has tannins on the outside, which prevent anything from eating this wasplet, because the oak gall is going to be, toxic to the herbivore, but not to the herbivore. Anything that's eating the oak gall, really. Toxic to the attacker, but not to the wasp. Any animal that tries to eat it is going to encounter the tannins. So the wasp can live in safety in this oak gall, provided with room, board, and defense. Problem is, the tannins, they're not effective against other plants. And there's a type of plant here called dodder, and what that does is it's an ectoparasite of the oak. So while the wasp is an endoparasite, the dodder is an ectoparasite. And this ectoparasite is going to actually seek out parts of the oak plant that have a higher amount of nutrient flux. This would be, for example, the galls. So this dodder is actually going to find the oak galls, and it will actually feed on the oak galls as an ectoparasite. This means for the wasp that this vine is actually going to take the nutrients that would be for the wasp and take them for itself, which kills the wasp. So this is two parasites competing for a host, and one ends up killing the other because it sucks all the nutrients away. Kind of a cool story. All right, then we have something called social parasitism. This is where it's parasitism, but it's not like they're sucking nutrients away from the organism. So we have some bird examples here. Cowbirds and cuckoos are both social parasites called brood parasites. What they'll do is they will lay their eggs in the nest of a bird, and they will harass the bird. If the bird, say, avoids the nest, they will actually harass the bird. So they will force that bird to feed their chick. And this is the cuckoo chicks will actually have like divots in their back where they push the eggs of the host out of the nest and take all the food for themselves. Now this can mean that they're very prolific birds because they don't have to produce eggs and then care for them. They just have to produce eggs, which allows cowbirds to produce upwards of 40 eggs per year, whereas your blue-winged warbler is going to end up only producing 2 or 3. It'll have a fitness of 0. It will raise the cowbird chick instead, and that's your brood parasite right there. We get the term cuckold from this. When an individual raises an offspring that is not their own, it comes from the term cuckoo or cuckoo. Here, your cuckoo chick is going to be raised by the host, not the real parent. And that's where we get the term cuckold, someone who raises another kid that's not their own, usually when they have been fooled into such. Then there are kleptoparasites. Kleptoparasites are thief parasites. what these frigate birds will do is they will find some honest, hard-working bird that has been hard fishing all day and is bringing its fish back to its nest. And these birds will dive bomb it until it loses that fish, and then they'll take the fish. So that's a kleptoparasite as a form of social parasitism. I was going to compare parasitism here to mutualism. For both of these, you have an intimate interaction. You have an intimate interaction between the organism and its host. So a parasite ideally doesn't kill the host. If a parasite kills the host, then, well, it's out of room and board. So a parasite generally reduces host fitness to increase their own fitness. But if they increase host fitness, they may be able to increase their fitness too. And what you essentially have is a balance. Reduce the host fitness and increase your own, but you might kill the host. If you decrease your fitness a little compared, but that brings the host fitness up, it may actually be closer to optimal because less often the host dies. So a good example of this is Wolbachia. So Wolbachia infects mosquitoes, fruit flies, and other flies, really. Wolbachia, if a male infected with Wolbachia mates with a female that's not infected with Wolbachia, there will be no eggs. A female, I think it's a female that begins life infected with Wolbachia, will actually be able to lay eggs, but all of those eggs will be infected with Wolbachia. So it's 100% male fitness decrease, but female fitness nothing, if I'm remembering this correctly. What I do remember, though, and I was just looking this up beforehand, so I don't remember more. Wolbachia increases the fitness of their host by making some fruit flies less preyed upon. They make them more resistant to pesticides, those are the bigger ones, and more resistant to other bacteria. So these hosts actually become more resistant to other things like pesticides, and they're going to live a little bit better. So because they live a little bit better, they can actually have a greater number of reproductive cycles in which they pass on the Wolbachia parasite. So increasing host fitness is a mutualist. Decreasing host fitness is a parasite. And this back and forth can actually be cases where parasitism evolves into mutualism, or where mutualism evolves into parasitism. We see cases where bees will take pollen from a plant, but not pollinate the plant. They'll just eat the pollen. That's a parasitism, or predation, actually, because it's eating gametes. A mutualism is where the bee will take pollen from the plant and give it to another plant. That's a mutualism. So there is a balance between parasitism and mutualism in evolutionary interactions. There's also a balance between parasitism and extinction called the Red Queen hypothesis. The idea here is that a parasite must avoid detection by the host. If a parasite has genes that has alleles that allow it to be detected by the host, then the host will destroy it and there's zero fitness for the parasite. The host, on the other hand, must avoid parasitism. If the host has alleles that allow it to be parasitized, it'll lose fitness as well. So there's a lost fitness for parasites that get detected and for hosts that fail to detect. So both of them have increased fitness for detecting the parasite and for failing to be detected. So this back and forth means that both populations are evolving very quickly. But the interaction doesn't change. The moment the host begins to detect the parasite, there is now strong natural selection on the parasite to avoid detection. The moment the parasite evolves to go undetected, there is now strong natural selection on any alleles that confer the ability of the host to detect. So the Red Queen hypothesis comes from this Alice in Wonderland example, where the Red Queen must run faster and faster just to stay where she is. And the Red Queen hypothesis is that parasites and hosts are in an evolutionary race just to stay in their same interaction. And neither wants to be in a race, but they both are because both wants to get rid of the other. Then there's parasites that can manipulate their host. So you have here a type of pill bug. And the pill bug, if it is infected with a, Plagiorhynchus. If it's infected with Plagiorhynchus, the pill bug is no longer afraid of the light and will go out in light areas. Now, if it goes out in light areas, it's going to be preyed on. That's why it's afraid of the light. If it goes out in the light, it's going to get eaten by a bird. So, it's no longer afraid of the light. What does it do? It goes out and gets eaten by a bird, which is exactly what the Plagiorhynchus wants. Because now the Plagiorhynchus is going to lay eggs it's going to mature in the bird, it is going to lay eggs in the bird, and the eggs get shed with the feces. When they get shed with the feces, they'll eventually get eaten by a sow bug, pill bug, whatever. And that pill bug will then become not afraid of the light. And the cycle continues. Toxoplasmosis is something that infects rats. So it infects a rat and makes the rat actually like the smell or be less afraid of the smell of cat urine. So if it's less afraid of the smell of cat urine, now it's going to go in places where cats are, and the cats are going to eat it, of course, because that's what we hired them to do. And if the cats are going to be eating these rats, then the toxoplasmosis gets passed into to the cat, and then shed in the cat feces. This is why pregnant women should avoid changing cat litter, is because these toxoplasmosis, when they infect a pregnant woman, they can actually damage the developing embryo and cause a miscarriage. So that can be dangerous enough, but also it's considered right now. And click on the link and give that thing a check out. It's believed that the crazy cat lady syndrome is actually because women who have been infected with toxoplasmosis now aren't really afraid of the smell of cat urine. They even enjoy it, and thus they go and get themselves more cats, which is an interesting way of thinking about it. Parasites might also alter the host morphology, so not just behavior, but shape. So this is an Arabis species, it's a type of mustard, and Puccinia monoica is a fungus that infects these, but has to infect them by pollinating. So it infects the flowers, really, and then the seeds will go on to create infected hosts. So what happens here, this infected host will form what looks like a flower. And to most insects, that looks enough like a flower. The insects will land on that. They'll get pollen, which is actually Puccinia spores, and they'll pass on those Puccinia spores to real flowers, which infect the seeds, which cause more of these fake flower plants. So here's a parasite that will destroy its host, yes, but alters host morphology and thus continue. I want to point out that this is probably more in microbiome, definitely more in evolution, so I'll cover more in those classes. Well, I won't cover it in microbiome. Someone will. Dr. Kobe, right? So pathogens, plagues, and populations. A bacteria needs to be able to infect a host, needs to be passed on to its hosts. And once it's in a host, now a pathogen is just a parasite that causes disease, often a bacteria or virus or fungus. Is a pathogen. So we're often in the realm of microbiology, we're talking about pathogens as opposed to parasites, which are macrobiology. So a bacteria needs to stay in the host long enough to be passed on. We call that the R number. What is the R number is the number of new hosts infected by a pathogen. An R of 1 means that each host is going to give rise to a new infection. An R greater than 1 means each host is going to give more than one infection. So there was a report on the radio once that in Eastern Washington, the R for coronavirus is 1.12. What that means is for every one person that is infected with coronavirus, 1.12 new people get infected with coronavirus, which means this population of pathogens is rising. Now, something like measles has an R of 9, which means if you have one person infected, 9 people will get infected. And then the next generation will be 81. And then the next generation will be a larger number, 9 times 81. I'm not mathing right now. But this is, a goal of this is to infect more hosts. Well, that also means that the bacteria has to be able to not kill the host. If it kills the host, then the host is not passing anything on. For Ebola, the R is, I think, like 0.09, something very low. It's less than 1. So Ebola, unless a lot of people are coming and touching the corpse, Ebola is not going to pass on. Now, I say a lot of people touching the corpse because that is actually a tradition in the areas where Ebola lives. Because people will touch the corpse of a dead one, and they'll actually get Ebola on their hand, and, that spreads it. But in places where that custom is not present, say Europe, Ebola generally doesn't spread. So that prevents Ebola from being a good pathogen. Let's think, common cold versus pneumonic plague. Pneumonic plague is passed on by aerosolized droplets. It kills its hosts pretty often. I think it's 100% death rate, or at least 25% death rate. It's high. It's high death rate. The common cold is passed on by droplets. It kills almost 0% of its hosts. So how many new hosts can a cold infect? Well, just go to a daycare. How many new hosts can a pneumonic plague infect? Fewer, which makes the pneumonic plague a worse pathogen than the common cold. So here we have a picture of bubonic plague and chaos everywhere and all of that. That can devastate a population, but in the same of doing so, it can also devastate its own population. So mismatches between pathogens and hosts can kill the host and the pathogen. It's best for a pathogen to not kill its host. Then we have parasitoids, a very special and wonderfully grotesque. Very special and wonderfully grotesque type of parasite. And what they'll do is they will grow inside the host. The parasitoid will spend its whole life cycle, or at least its juvenile cycle, inside the host, and it'll actually burst out of the host when it leaves. So you'll have these wasp will lay its egg in a caterpillar. The egg will develop in the caterpillar. The larvae will eat the caterpillar, but not essential systems. It will eat the fat. It will drink the blood, won't touch the nerves. When the caterpillar goes and forms a pupa, then the wasp will just go whole hog and eat everything. And then it will emerge from that pupa. If you ever collect a lot of caterpillar pupae, you're actually going to hatch a lot of moths or butterflies, and also a lot of wasps. This is very common. And another good example of this is that John Hurt moment. That is a parasitoid. Yes. That wonderful alien species, its youth stage would be counted as a parasitoid because it grows and feeds on the host, parasite, and then bursts out of the host, which makes it a parasitoid. All right, so there's a whole bunch of different ways that organisms can exploit each other. That was kind of a fun romp through this, and there are plenty more examples out there for you to enjoy. I've put some YouTube links in there, and I really hope you go out and look at some of these interesting predators, parasites, and parasitoids. Enjoy.